Hello all. This lecture includes the summary of space-time block codes. The basic structure of this space-time code is illustrated in this matrix, where this uh, T, capital T, is equivalent to n, number of time intervals, right? And this n, capital T, is nothing but the number of transmitter antennas which we used to represent it the small n and small t, right? So here the each column represents the time slot and each row represents the transmit antenna, right? As we all already know about the benefits of space-time block codes, main benefit that it does not require the channel state information at the transmitter, whereas provides the full diversity, the maximum diversity attained with the system having channel state information can also be attained with the help of space-time block codes. At the other hand, it reduces the complexity of a ML decoder, uh, right? Uh, ML decoder, it's a constellation size raised to the power nt is the number of cases, right? We are getting this is the complexity. Now it will be going to reduce with 2m, or you can say that ntm. So instead of exponential increment, it is linear now, right? In this diagram, it shows the transmission of LMOT space-time block code, which is a special case, provides the full rate and full diversity. However, it incurs a loss of 3 dB in comparison to the transmit beamforming due to this unavailability of the channel state information at the transmitter, right? So in the first time period, transmitter 1 transmits x1, transmitter 2 transmit x2, and the second time interval, transmitter 1 transmit minus of x2 conjugate, transmitter 2 transmits x1 conjugate, right? Here this r is equivalent to this y1 and this is equals to y2, right? And vector or matrix form, vector or matrix form, we can represent it like this, where this H is an effective matrix and this norm of H is nothing but mod of H1 square plus mod of H2 square, right? As I told you, this is for decoding complexity for LMOT. You can say that it reduces from m raised to the power nt to O2mt. For LMOT, you can say that you can re-verify it with your analysis about the number of cases. Like it provides the decoupling. It is due to this fact. It is due to this fact we can reduce the decoding complexity from m raised to the power nt, in this case nt2, right? From to ntm 2m, right? Another higher fractional order orthogonal STBC is given as this, where G3. G3. Why we are using here G instead of X? Because we are heading towards the generalized OSTBC, right? So, what can you say about the rate of this particular code matrix? How many symbols are there? Three, right? Three symbols. NS is 3. And what about the time intervals? Capital N, it's 4. Right? Similarly, here it will be again 3 by 4. Right? So what is the main difference between these two? Rate is same, strength. Anything else you are observing here about this dimension? So what happened with the dimension? Right? So see here in this table, for LMOT, how many number of transmit antenna we need? 2. NS is 2, and total 9 time slots is 2 also. The rate is 1 for LMOT. Similarly, for G3 matrix, which is shown above, how many transmit antennas? See, in the first column, we need 3 transmit antennas to transmit X1, X2, and X3. Transmitter 1, transmitter 2, and transmitter 3. Right? Whereas in G4 we need 4 number of transmit antennas. Except that everything is same here. So as we increase these time slots, channel needs to be remain constant over this particular time intervals for whole block. We are assuming that the condition of channel will not going to be changed or remain static for these 4 time intervals. It's quite obvious as we increase the number of time slots here, rate would decrease, and at the other hand delay will be also going to be increase, right? Now how we can design a generalized OSTBC design? So this is a basic formula to design any OSTBC, right? For example, for k equals to 1, it means there would be two symbols x1 and x2, right? Now it will be equivalent to G2 x1 comma x2, right? And this will be for k equals to 1, it become G1, it become G1. I is identity matrix. I1 here is here 1, x2 is there. G1 is nothing but would be equivalent to x1 only, right? So first element will be x1, second element will be x2. This will be minus of x2 conjugate. So it will be look like this matrix x1, x2 minus of x2 conjugate, and here it would be x1 conjugate again, right? Due to Hermitian, due to Hermitian. So it is also a Alamoti STVC, but it's a rotated version. If you are observing it, it is a rotated version of Alamoti STVC we have studying so far, right? So for k equals to 2, you can also design another orthogonal STVC. Oh, so what about for if the number of transmit antennas is not a power of 2, for example 3 transmit antennas and this, For that, we need another processing by deleting the sum columns. Don't need to be a worry about this. This is not in your syllabus. This is just for the sake of the knowledge. I'm sharing it, right? So now here's one more example where k is equals to 7. How much would be the case? Sorry, k is 3 here. So k is 3 means x1, x2, x3 and x4. Four symbols we are looking to transmit. And if we put this k equals to 3 here, what we will get? We get 2 raised to the power 2, 4, g4, x1, x2, x3 accordingly, right? Similarly, another thing. So we have already seen the structure of g4 here. So we need to substitute this value of g4 here, or you can again find out this g4 with the help of this formula. So it's a kind of recursive thing. So by substituting the value of g4 here, what we will get? This thing. So try to find out the rate of this particular OSTBC matrix, right?